Hi, this is Mathias from Partisia Blockchain. In this video, I'll give a short and intuitive introduction to different encryption technologies that's used for privacy-preserving computation. We will talk about secure multi-party computation, fully homomorphic encryption, zero-knowledge proof, trusted execution environment, and differential privacy. All these technologies, with the exception of differential privacy, are dealing with secure computation on data. And at a high level, this means that they can be used to perform any arbitrary computation on one or more pieces of data while all keeping it private. So first up is secure multi-party computation, also known as MPC. This is probably a technology that you heard about if you follow Partisia Blockchain. It's a cornerstone in our infrastructure. It's a technology that our team helped groundbreak. MPC is a fairly broad class of protocols that enables two or more parties to compute a function on privacy-preserved data while revealing nothing except from the output. The MPC protocol typically follows three phases. The first phase is that the input is privacy preserved with a technique called secret sharing. So secret sharing divides the input into different secret shards. The next step is that these secret shards, they are distributed to the MPC nodes. Then the MPC nodes will carry out the computation, and the output is fetched back to the input, or in many cases to the users, which then can decrypt the output and share it with whom they want. The protocol relies on a non-collusion model, so the secret shares will have a threshold, which could be that you need to recover 2 out of 3 secret shares in order to decrypt the data again. Next up is fully homomorphic encryption. This technique solves a very old problem, and the problem is, can I encrypt data and then carry out computations on it? So the technique solves it by allowing to encrypt the data into ciphertext, and then the data can be shared to a server, which can then carry out the computations without revealing the data, without revealing any privacy, and then share back the results to the user, who can then decrypt it and share the output with whom they want. The protocol here relies rather on clever cryptographic computation, whereas MPC relies on clever cryptographic protocols. It also means that fully homomorphic encryption requires less data to be sent between different servers, because this is only a relationship between a client and a server. In practical, it's slower than MPC, and it's also a relatively new technology that only came out around 2019. It's a very interesting technology that we also work with in Partisia, and we actually support it as a layer 2 solution because, as I mentioned, it only requires a client and a server relationship. Next up is zero-knowledge proofs. And zero-knowledge proofs are different than MPC and fully homomorphic encryption in the sense that they don't carry out functions or general computation. They can produce an output which will either be true or false. So the easy use case for these zero-knowledge proofs is for digital identity, for example. So let's say you have a credential which contains your age. Then you can wrap that up into a zero-knowledge proof and only present to a verifier whether you are more or less than 20 years old. They are very popular, and it's a very hot topic. They come in different varieties, such as CK Snarks and Starks, and they are being practically implemented in, for example, layer 2 protocols with CK EVMs. It's a technology that's complementary to what we do in Partisia, because there's a lot of digital identity projects that want to build on our infrastructure, and this technique is rather complementary to a MPC than a competitor. So for example, you can use zero knowledge proofs to prove a statement is true or false, and then the verifier can enhance that with MPC by, for example, taking in private biometric or images to enhance the verification of that process. Then we have trusted execution environment, and this technology is different than zero knowledge proof, MPC, and fully homomorphic encryption in the sense that it's more focused on the hardware. So with trusted execution environment, you can have hardware with a secure enclave, and then when the data is inside that enclave, it can perform private computation and remain secure. And lastly, we have differential privacy. And this technology is radically different from the previous technologies we talked about. So MPC, trusted execution environment, fully homomorphic encryption, all of them provide a means to compute something on private data. And they don't really take into consideration what that something is. So that's also why when we use these technologies, we have to be very smart about what we compute and what the output is, and who we reveal it to. Because, for example, when we train machine learning models, there could be a way to reverse engineer it to reveal certain aspects of the privacy. So that's why we always need to be careful and smart about designing these systems. Differential privacy tries to solve this and guarantee these privacy primitives by adding noise and synthetic data into the calculations. So if you put it compared to some of the other technologies, this is more about producing an output that doesn't reveal too much, whereas, for example, MPC, fully homomorphic encryption, and trusted execution environment, they reveal nothing except from the output, whereas differential privacy reveals something about the output.